Good break. Let's just say break it all. Midterm break tends to not be a break. Everybody catching up on projects and things like that. All right, so slight change in syllabus. We did in the last lecture. We covered some spectral analysis of operators, and we focused on discrete spectra. Right? And the natural thing to do would be to go on to continuous spectra, but it's kind of a half lecture on continuous spectrum, and I didn't think that it was worth. I didn't think that it contributed enough to constitute its own lecture. Moreover, I would like to speed up a little bit so that we can do some more interesting stuff in the back end of the course instead of focusing on. I really want to get to differential operators, and in particular integral representations of solutions. So, in that vein, today I want to focus on some formal properties of linear differential equations. Now, it might seem like, we've seen differential equations and certainly linear differential equations, more or less from first year. So, the question would be, what new is there to tell you about these differential equations? And I hope that I will convince you that there's still quite a lot new that I can tell you about differential equations. First order linear differential equations. Okay. So most of this lecture is going to be focused on first order linear differential equations. And in particular, how we classify solutions of those first order linear differential equations by the properties of the coefficient functions of the differential equation. So I have some differential equation, dw by dx plus some p of x times w equals 0, right? Seems like a straightforward enough differential equation, and plus first order linear differential equation you can solve more or less trivially, either by separating them or using an integrating factor. But what I want to show you is that the solutions of the differential equations themselves can be classified according to the properties of the coefficient functions, like p of x multiplied w. Okay. And we'll do all of this stuff for first order linear differential equations, and then we'll move on to a general nth order linear DEM. I'm not going to pay too much attention to this because essentially all the data and all the properties that we read off here will translate naturally into this situation here. And in particular, I'll tell you about something called the monotropy matrix associated to the differential equation, and how it encodes these properties as well. So, by now, you will probably have built up a substantial toolkit for solving differential equations. Okay, all of you. And you've learned lots of tools and techniques for finding solutions of differential equations. And they're usually ad hoc techniques. I give you some differential equation, stare at it long enough, and some strategy that you solve the differential equation. And as I said in a kind of cheap way the last time, pretty much all we do as theoretical physicists is really study differential equations and its solutions. And so it's important to understand the properties of these differential equations. As I said last time, that I'm not really interested in any particular equation. I'm interested in the differential operators. I'm interested in thinking of differential equations as eigenvalue problems, right? And seeing what I can learn from bringing to bear on these eigenvalue problems, the toolkit afforded to me by the algebra. Okay. So, one general, very powerful method for solving differential equations, you may have learned already in first year, or second year, is Frobenius' method of power series. So basically what I do is I power series expand the function that I'm trying to solve for, plug it into the differential equation, and that will give me some essentially recursion relation for the coefficients of that function. If I can solve those recursion relations, I plug them back into the power series expansion, And if I'm super lucky, then I can resum the thing and I'll find an analytic solution. I don't necessarily always have an analytic solution, but I can always do this Frobenius method of power series expansions to solve differential equations. This method is a bit limited. It's limited to the domain of convergence of that power series. Okay, so I'm only able to tell things about the solution within some small domain within which that power series converges. Okay. But if the power series converges, then one of the things that you would have learned is that the convergence of the solution is related to the convergence of the coefficient functions of the differential equation. What I want to do today is push this a little bit further. I want to ask, can I tell things about the analytic properties of solutions to the differential equation by just looking at the coefficients in the differential equation itself? Right? Do I get some hint as to what my solutions are going to be doing by just staring at the differential equation? Right? Let me give you a simple argument to convince you that that very superficially, I should expect that the coefficients of my differential equation encode properties of the solution to the differential equation. Right? Then I'll do this by means of an example. And again, I want to emphasize that the point of this example is not to solve the differential equation. Do this in your sleep, I understand. The point is to extract lessons from it that we can then port to more general circumstances. So let's consider the following differential equation. Let's say du by dx equals u squared. It's not a linear differential equation, but I don't really. We'll get to the linear differential equation shortly. So I can solve this equation because it's first order and it's separable, and we can take all the u's to one side and the x's to the other side, and I can integrate. In particular, this equation, let's call it equation. Is solved by the function u of x equal to minus 1 over x. And the solution holds for all x, all real x, except x equals 0. Okay. Well, technically, there's actually two solutions here. Because when x is less than 0, I have one solution. And when x is greater than 0, I have another solution. Because x equals 0 is excluded from the solution set, I have two sets of solutions. So actually, there are two disconnected sets of solutions on R minus and plus respectively. And if I restrict my attention to real value solutions to this differential equation, then there's no way to connect this x less than 0 region to the x greater than 0 region, because I have a punch-in line. Okay? So this is why they're disconnected. On the other hand, the related equation. dw by dz equals w squared also has a similar solution, where now z is a complex number and w is a complex valued function. So let's write that one. I'll explain. Also has a solution w equal to minus 1 over z. And notice that this solution is analytic. Everywhere except z equals 0. Same argument. Okay. At z equals 0, I expect this to blow up. And in fact, I have a pole at z equals 0. However, on the complex plane, the connectivity of the domain of W is not destroyed because I can always deform my path around z equals 0. So I can connect the x less than 0 region to the x greater than 0 region by just going around z equals 0. And what I did here was to analytically continue this differential equation onto the complex plane. Okay. All right. So that was just to make the point that I can do this. I can analytically continue a differential equation on the complex plane, and some of the properties of the real valued solutions can be avoided by utilizing the fact that the complex plane is a complex plane that I'm allowed to go around. Let me continue to make the point I want to make. So now, let's consider the differential equation. Let's consider the first order differential equation given by dw by dz. So first order complex differential equation given by dw by dz minus, let's say, gamma over z with w equals 0. I'm going to call this here this coefficient function p of z. And p of z depends on a parameter gamma. Notice that this coefficient function has a simple pole at z equals 0. I'm looking for a function w such that when I differentiate this function w, I get w itself with this factor of gamma over z in front of me. So the solution to this equation is w of z equal to z to the gamma. Differentiated once, we pull down the gamma z to the gamma minus 1, that's gamma z to the gamma over z, or gamma over z. rephrase this. Now I'd like to distinguish three cases depending on gamma. So if gamma is a non-negative integer or a negative integer or a non-integer, the solution does three different things. Okay. If gamma is a non-negative integer, fine, 2, 3, 4, 5, etc., then W of Z equals Z of gamma is analytic at Z equals 0. Okay. If it's analytic at Z equals 0, then we say that it has a regular point at Z equals 0. If gamma is a negative integer, like -1, -2, then my function looks like 1 over Z, 1 over Z squared, etc. Then it has a pole at Z equals 0. Or if it's a non-integer, like a half, so I have square root of Z, then it has a branch point. And Z equals 0. Okay. So the upshot here is clearly the parameter gamma in the coefficient function of this differential equation determines the nature of the solution of the differential equation. Right? So the parameters of the differential equation determine the analyticity properties of solution. That's the lesson I'm going to take away from this. Any questions? Yeah.
Not away with it. Are the solutions and regular points all branch points? what do they tell you about this DE? Do they tell you anything?
What do you mean by what they say about the? These are properties of the solution.
Solution that would that change the dynamics of the solution of what the solution is described?
Well, if I have a pole, if I know that my solution is a pole, so okay. It might be a little bit difficult to buy this argument. I've already solved the DE. All right. So I've solved the DE and I'm declaring the solution and I'm telling you that these are the properties of the solution of the DE. And look, they're related to the properties of the parameter. What I want to convince you of now is that, in fact, I don't need to solve the differential equation at all. This is a general statement that the parameters of the DE determine the elasticity properties of the solution. So even if I don't know how to solve the differential, right? So again, I'm going to move on to first order linear DEs and solve these DEs. But higher order differential equations are much more difficult to solve. However, these elasticity properties stay. Right? So this means that without solving the differential equation, you can look at the coefficient function and you can say, if this coefficient function with gamma is a non-negative integer, negative integer, non-integer, then the solution is going to have these properties, right? Without solving the DE. It's without solving the DE that's the key. Yeah. And I fully buy the fact that if I know that this is the solution, you know, okay, great, I can plot the solution and I'll learn the same thing out of this, right? My point is that I don't have to know what the solution is in order to be able to say this. Right? So this is a really strong statement, right? And so what I'm saying is that by studying the coefficient function, I can tell things about the differentiability of the function of the solution of the DE, right? When I say it's got a pole, that means it blows up at a certain point. Right? When I say it's got a branch point, that means that I have to be very careful about branch cuts at the complex point. When I say that it's regular, I know that it's a perfectly regular solution, it's an analytic solution. Okay? And again, all of these things I'm able to tell by just looking at the coefficient. So let's formalize this a little bit. So to formalize this argument, let's consider the first order linear differential equation dw by dz. And now I'm going to be working almost exclusively on the complex plane for all the reasons that I told you about just now. Plus some coefficient function p of z, w equals 0. And I'm going to assume something about this p of z. I'm going to assume that p of z has, at worst, isolated singular points. I don't know what the singularity is, but I'm going to assume that these are isolated singular points, which means that they're not dense. It has some poles or branch points, but whatever they are, they're going to be isolated. Means that I'm going to be able to draw some circle around these points of sufficiently small radius or complex plane and not encounter another such point. Okay, so if this function only has isolated singular points, what we can do is we can lower or expand this function about some point, let's say 7. So let's do that. I'm going to make the expansion between in the angular region consisting of points between R1 and R2. Okay, so the picture is just one of explain. This is one point. Z0. There's some R1. There's some R2. We're going to consider all z's that lie in this edges. Okay. So if I do this, it says that all z that lie inside this annular region there, I can write P of z that the sum from n equals minus infinity to infinity, some coefficients may n, times the equation. Question?
Sorry, I was just in this one. It's all good.
Alright, so let's take this guy and substitute the two here. Now, this is the first order linear DB. So it's so solve it by inspection more or less. Find a solution. W of z equal to some constant of integration times the exponential of minus the integral P of z dz. Right. You can differentiate that and check it. So now we substitute this lower expansion into here, and we'll find that this is equal to this constant c times the exponential, which I'm going to split up into three parts. This sum goes from minus infinity to infinity. In here, one coefficient is particularly special, and that's a minus 1. Okay, because that a minus 1 is the residue of z. You with me? Okay, so this is minus a minus 1 times the integral of dz over z minus z naught. And then I have an integral that goes from 0 to infinity. N. Integral inside z minus z naught n z. And then I have an integral where the sum runs from 2 to infinity. A minus n integral of z minus z naught minus n dz plus this. I can do all of these integrals. Right? This integral is a logarithm. This integral goes like z to the n plus z minus z naught to the n plus 1. This integral goes like z to the n z minus z naught to the minus n plus 1. So this is my integration constant times a minus 1 log of z minus z naught minus sum from n equals 0 to infinity, make n over z minus z naught 1, z minus z naught to the n minus 1 minus plus, sorry, sum from n equals 1 to infinity of a minus n minus 1 over n times z minus z naught to minus n, where I have shifted the sum by 1. And now I look at this expression and I notice the following. This first bit here is an exponential of the logarithm. So that just gives me a z minus z naught to the minus a minus 1. In other words, it's of the form c times z minus z naught to some alpha. Okay, where alpha here is really minus a minus 1, but I'm going to write that as alpha for a reason that will become apparent just now. And then I have a whole bunch of other stuff. The key point about other stuff is that it's analytic for all z. So if I can just write this thing as some g of z, where g of z is an analytic function. So again, I start off with the first order linear differential equation with some coefficient function as u only has isolated singular points. I can write that solution, w of z, as some constant, and don't really care about this guy, times z minus z naught to some power times an analytic function. Okay. Now, depending on this P of z, which is encoded in this Laurent expansion, depending on the structure of P of z, my solution will have different properties. So let's explore some of these properties and see if we can classify W of z based on the property. So, if P of z has one, a removable singularity, z naught. In other words, if the A ends A minus n vanishes for all n greater than or equal to 1, right? So A minus 1, A minus 2, A minus 3, etc. All the negative coefficients of all the negative powers of z all vanish. Then this is a removable singularity, and I can redefine my function to make it clear that it's not a singularity at all. Then W of z is just some constant times its analytic function g of z. And it's analytic everywhere. And we say that the first order linear dE has a removable singularity at z. The other hand, if P of Z is a simple pole, so all the A minus N's vanish when N is greater than 2, but A minus 1 is non-zero. Then W of Z in general, because this guy could not be an integer, be non-integer. The W of Z general has a branch point. The dot, and say that the let's call the linear DE as a regular singular point. At Z. Then finally, if it has a higher order pole, the pole of order m greater than 1, then W of Z has an essential singularity at Z naught, and we say that the linear DE has an irregular singular point at Z. So again, an irregular singular point is one where the solution of the DE has an essential singularity. Okay? All right. So again, even though what I've done here is expand on a solution that I've already worked out, because this is a first order linear differential equation, these conclusions follow with differential equations that I don't know. So, with some appropriate characters, which I'll come to just now. Okay. So the point I want to make here is that we've managed to classify the solutions of the differential equation. Right. And even though here I've done it, knowing what the solution is,